Well, I would like to introduce Professor Bas Edixhoven.
Yes, very good.
From the Leiden University, from the Netherlands. The title of this talk is Some Elliptic Curves from the Real World.
Thank you for the introduction. So I'm a mathematician, but I understand that this is maybe not everybody here is a mathematician. So I gave a very similar talk recently in Paderborn, in Germany, for the Department of Mathematics, Computer Science and Engineering. So I hope the talk is suitable for the audience here. Now this is a very small audience. You could consider it as a kind of private lesson. You are free to interrupt and ask questions. Yes. So
it was a mistake to say that.
We will see. We will see. Yeah. So some elliptic curves from the real world, right? Because I think on the first slide I explained that elliptic curves are what I very often work with. They are important for my own research in number theory and arithmetic geometry, but that's not what I want to talk about today. But there are also other ways in which I encounter elliptic curves. And this happens even outside mathematics, as we will see at the end of the lecture. I went in some museum in Spain, and I saw a surface there, and many people must have seen it, but nobody had really asked the question, what kind of surface is this? And it is related to elliptic curves. So I do not assume that you know anything about elliptic curves. I'm going to give a kind of introduction to them. I understand that in the past, maybe also Christian
I gave a talk, yes.
gave once a talk, and
I think we'll see the same pictures that I
No,
drew. Will be here.
No.
It was a different subject. Absolutely.
it was.
No, it was.
No.
Yeah,
You will see. You will see. Well, you will see. So I will give a few examples. One example is from quite old projective geometry by Poncelet, a French mathematician. So that is plane geometry. There is also in Escher's paintings. I think you have seen a few of them. They are always of these impossible kinds. And here is a very strange one. It comes from elliptic curves also. And this was discovered by two colleagues of mine in Leiden. And also classical mechanics. So this goes back in history again, right? Euler is, I think, around 1700.
1740.
Yeah, well, so maybe more appealing to a physicist here. Who are physicists? Are there any physicists? Mathematical physicists? Okay. And the last one is in the, as I said, in a museum in Spain. Minimal art by a person, an artist called Richard Serra. And I think that my reason to lecture on this a little bit is the last example, because I thought that I should tell the world that this is also an elliptic curve. I will put the notes on my homepage, so the PDF at least, you can, if after the lecture I will put it there, you can download it if you want. And then we start with the elliptic curves. So one way that elliptic curves arise is as plane curves. So you take this equation where a and b are parameters. So you just take your favorite numbers for a and b. But you want this to be non-zero. That means, actually, what does it mean that this is non-zero? It means that this cubic function, this x cubed plus ax plus b, has no double root. It is the discriminant of this polynomial of degree 3. So you want that to be non-zero for a reason that will show up. And you look at the set of solutions in the two-dimensional real plane. So here are two examples. You could take here, I don't give you the a and the b, but I give you the degree 3 polynomial. Maybe it's not even. This has a peculiar property, namely that the coefficient of x squared is 0. And I don't think that is true here, so I cheat already. But it is true, of course, that you can translate it with the x coordinate, so that the term of x squared, the coefficient of x squared, becomes 0. You can put them in that form. And here you see that this degree 3 polynomial can have 3 different real roots. Then you get a function, so then you get 2 components, because this cubic polynomial is negative if x is very negative. So if x is -1, then it becomes 0. Then here it goes up, and then goes down and goes up. So here and here you cannot take the square root as a real number, because the function on that side is negative, but it has a positive part, then negative, and then positive again. So it looks like this. Here it is a 1 that obviously has only one real root, namely -1. Yeah? And then the other 2 are imaginary. And then it has this shape. And if you are in between, I mean, there is this condition. We wanted this expression to be non-zero, because it being 0 means that you have something like this or like this, that this degree 3 polynomial has a double root, but not a triple root. Then you get this picture. And if it has a triple root, so this is called the double point, and this is called the cusp. And you get that. But they are clearly different from the other ones. These are singular, right? At this point, or at this point, the solution set is not a manifold, and that is the complication that we don't want today, right? And so if you have any non-singular degree 3 curve in R2, so if you would take a more complicated equation with x and y, a polynomial in these 2 variables of total degree 3, then you could always bring it in Weierstrass form by projective transformations. So I don't want to go into that technical thing, but I just want to say that the equation that we look at looks a bit special, but in fact it is a kind of standard form for the general equation. So, okay, so, and how are we going to look at these elliptic curves? Well, with the point of view of an algebraic geometer. So I have to say a few words about algebraic geometry. So what does an algebraic geometer do? He looks at what he called closed subvarieties in Rn. And they are solution sets of systems of polynomial equations. Right? So we write systems of polynomial equations and we look at the 0 sets. Right? Those are called algebraic varieties, closed algebraic varieties. When you study objects, you also give the relations between them. That means which maps between them do you want to consider. And our maps should locally be given by rational functions that have no poles at the points where we evaluate them. So rational functions means quotients of polynomials, f divided by g. Those are the maps. So if we take a map from Rn to Rm, we can consider m of these rational fractions, and they, whenever we want to look at them in some point, they should be written in such a way that at that point the denominators are not 0. We don't want to divide by 0. And what locally means is specified here. Locally usually refers to a topology. And this is not, we are not going to use the topology that you are used to. So the topology that algebraic geometers use is called the Zariski topology. And that is the topology for which the closed subsets are exactly these sets given by polynomial equations. So that is a bit weird, but it is the natural topology for the maps that we want to consider, because we want that the denominators are not 0, so we cut out the set of solutions of the equations that you get by putting the denominators equal to 0, and that is a closed set, and the complement is what we call open. And that's why we look at this topology. So it's also true that this topology does not refer to distances or things like that. So we can also work with complex numbers if we like. So algebraic geometers have the habit to not only consider real numbers, but actually complex numbers are easier for us. And not only is the complex Cn space not good enough for us, we want to have projective space. Now, I'm not going to say much about projective space. We will see a picture of it. I mean, what happens in a picture. It is somehow, in analysis, you like compact sets better than arbitrary sets. And for an algebraic geometer, the projective space has the same properties as a compact topological space for people in analysis. Okay, so, and because everything is formulated just in terms of polynomials, we can even replace the field of complex numbers by any algebraically closed field. We could take fields of positive characteristic, and in fact people work in such a generality that they can replace the field by any commutative ring. But that is a technical thing, and it's not what I want to do. I just want to mention that algebraic geometers do that. So like Christian, I think he likes that very much, that you can take any ring and do this kind of geometry. Okay, good. So now I want to give you a fact. So the first fact, so the title of the slide is that elliptic curves cannot be parameterized. So to explain that, or to illustrate that, let's first look at something that can be parameterized. So and if you take a non-singular degree 2 curve in the real plane, then it can be parameterized, and that is something that you have probably seen in one shape or another. So if I take a circle, so the equation for the circle is x squared plus y squared equals 1. 1, 2, 3, 4, 5, 6, 7, 8. We're now 7 now. Welcome. Yeah, the circle is an example of a non-singular degree 2 curve in the real plane, and I say that from my algebraic point of view, algebraic geometer's point of view, the circle is somehow isomorphic to the real numbers, to the line. And why is that? Well, we can take a point on the circle, this point, minus 1, 0, and we can look at all the lines through it. So that's what the slide is saying. You take the lines through this. So the lines through this point are the lines of this form, where the A is the slope of this line. And so the A is the same as the height where it intersects the y-coordinate axis, right? Because this distance is 1. So the slope is this divided by that. That is the A. And each line through this point, because this is if you parameterize it like this, and then substitute y equals a times x plus 1 in the equation for the circle, you get an equation with only x. And this is a degree 2 equation, because y is of degree 1 in x, and x also, and if you substitute it, you get something of degree 2, but it has a 0 at x equals minus 1. So it has an other 0, and you can just compute it. And I did it for you. That's this. And you see that you have a nice parameterization of the circle, right? Because for every a, I get this point on the circle. Maybe to get the point minus 1, 0 itself, a has to go to infinity, right? Because that is the vertical line. All the other lines, they intersect in another way. But you have that. And so I have this map from the real numbers to the circle, sending a to this. And that is, you can also write down the inverse if you like. That is also given by polynomials, or by rational functions. And I'm not, so that is, this illustrates my point, right? That an algebraic geometer looks at 0 sets of solution sets of polynomial equations, and the maps that he looks at are given by fractions, by rational functions. Okay? This is an example. And now there is a fact. So if you take an elliptic curve, so an elliptic curve was given by a degree 3 equation, then you cannot parameterize them, not even locally, by rational functions, using rational functions with a line. And the reason is that if you take that the equation is of degree 3 and not 2, So if you take a point on this curve and you take a line through it, then yeah, then it will intersect in 2 other points, because the total number is 3 normally. It's a degree, so, and not 1. So you can't do that, right? And in fact, if you count, so you know that if you have a polynomial in one variable and you count the zeros, you get as many as a degree. But then there are 2 conditions. You have to count with multiplicity and with complex numbers. And the same is true here. If we use, well, here, if we count with multiplicity and we use the projective plane, which I will illustrate, then each line intersects in 1 or 3 points. And here is the picture of the projective plane. So this is a, so this, you know that you get, you have to include the horizon to do projective geometry. So this is what happens. So here the curve is this red thing is drawn on say a tiled floor. You have a tiled floor, and then you look at it not really from above, but you are standing like this, and you see a horizon, and this curve goes to the horizon, and it has an extra point. And so for example, a line like this will intersect it in 3 points, right? If I do this, 3 points. But if I take a vertical line, then I have only 2 points, except that you also get that point at infinity. So in the projective plane, each line will intersect it in 1 or 3 points, and that's how it is. So, and so E of R stands for the set of solutions of my equation in the projective plane. So it also includes this point at infinity that for some strange reason is called 0. It should be called infinity, right? It's an infinity, but it's called 0. So, or yeah. And that is for all those lines in the vertical direction. So, now, so we cannot parameterize this curve. This is a fact of life. If you take a first course in algebraic geometry, then you get a proof of this. So I did not give you a proof, I just said, why does it not work? The trick that we did for degree 2. But you can prove it. But nature gives us something else instead, which actually is much more useful. So if we have 2 points on this curve, P and Q, then you can do what everybody would do, draw the line through P and Q. And now I said, well, each line intersects it in 1 or 3 points. But this one already intersects it in 2 points. So there is a unique third point. And that is this third point of intersection. That is called R here. So R is given if you know P and Q. But R is not, so wise people say, well, it's better to do another operation after that, draw the line from R to this point 0 at the horizon, and take that point of intersection and call that P plus Q. So that is a kind of strange thing to call that P plus Q. That needs to be explained. Why do we do that? But it is an operation on the set of points. Right? If you have a P and a Q, you can say, well, then that produces for me a third point, this point here, there, and that is what you call a binary operation. And the marvel, the miracle is the following, that this operation makes this set of real solutions, of real points of the elliptic curve, into a commutative group. I think even if you do not know group theory, the group axioms, I think maybe I list them here. No, I don't. So actually, okay, so I should explain what that means then, right? So making that into a group means, a commutative group means that if I interchange P and Q here, I get the same result. Well, that is quite clear, because if I call this point P and that point Q, then this line is still the same. That's easy. It also means that if I take one of these points, if I take the point Q equal to the point 0 at infinity, then actually the resulting point will still be the same point P. It means that the 0 is the 0 for the addition. That's why we call it 0. So why is that? Is that easy to see? I think it is quite easy, because if I take it, for example, 0 plus q in this thing, right? Then I have to draw the line from q to 0, and this will intersect it more or less here. But then the recipe says, then you should take the line from this to that point and go, then you're back. So you're back. But what is not easy is what is called the associativity. So the group law, saying that it is a commutative group, means that if you have 3 points, now I would have liked to have a blackboard, but if you have 3 points, say P1, P2 and P3, you first add P1 and P2 with parentheses, and then you add P3 to it, you get the same result as first adding P2 to P3 and then P1 to it. That's a very non-trivial thing. That is pretty hard to prove. But it's true. I would also like to mention the guy who made this very nice picture. He's a French guy. He was director of the Palais de la Découverte in Paris. And he is a professional picture maker, I think, because to make a picture of the projective plane like that is very good.
He's a mathematician.
Yeah.
Sure. Yeah. So he knows how to do it.
Well, that's not true. I have not seen other mathematicians do this picture. Maybe people can, but they don't do that.
Right.
But they should, I think, because somehow, if I would have to explain what the projective plane is, well, I think the people who know would be bored, and those who don't know wouldn't know it. So now, but projective geometry is also exactly the geometry that people discovered in perspective drawing. So in Italy around 1500 or so, 1500, with exactly these kind of tiled floors. And it's really better to make a drawing like this. So how am I doing on time? I think it's okay. So I can show the associativity of the addition in this group law in a particular case that is actually not allowed in my elliptic curve definition, but we can of course do some experimental mathematics. We could say, well, a degree 3 curve can be also the union of a curve of degree 2 and a line. If I look at the equation that say x squared plus y squared minus 1 times something else, that gives me a line, then I also have a degree 3 equation. I can look at what it means. So here I look at the case where my elliptic curve is not really an elliptic curve, is the union of the circle and the line on the horizon. So in the projective plane you have a line on the horizon, and the union of that is also of degree 3 in the projective plane. And I can convince you, I think, that in that case the P plus Q, so the P comma Q gives me P plus Q, is an associative operation. Because what happens here? I have to take a point on my curve, so I take this point here now, which is not at infinity, but here, this is a point on my circle. And I have a point P and a point Q, and I have to draw the line, okay? That's this line. And this gives me a point, well, it does not intersect this curve in the third point. But it does intersect the line at infinity in a point, namely the point at infinity of the horizon that stands for this direction. So if I draw from there a line through O, I get, by definition of the projective plane, a line through O, that the unique line through O that is parallel to this line. And then this is the P plus Q. But you see from the picture that it is symmetric around the perpendicular to this. So this angle here is also this angle. And so the point P plus Q that I get is angle from 0 to Q plus the angle from 0 to P. And so I'm just adding angles. That's an associative operation, right? So that is no proof that in the general case it is associative, but at least it is a strong indication. Yeah? Questions? No? Nobody? Okay, then we go on. So, but then we go to look at complex elliptic curves, right? I said algebraic geometers also have to look at complex numbers. And of course then we can draw the solutions, right? Because if we have an equation with two variables, then each of them is complex, so actually this takes place in R4, which is a bit higher dimensional than what we are used to. So, but I say that if I take the solution set in the complex projective plane for a degree 3 equation, as before, I get something that is homeomorphic, so isomorphic topologically, to a circle times a circle. Then a circle times a circle is the boundary of a donut, right? So why is that? And there are 3 reasons. So you can be a topologist, and I think this is maybe too complicated an argument. I don't know. So you could say it's compact. Well, that's easy because the projective plane is compact. Oriented because it is a complex thing. Connected, well, okay, you have to prove that. It has a Lie group structure. Yeah, I showed you that it is a group. And so it has a vector field without zeros, and then there is a theorem by Poincaré and Hopf that says that the Euler characteristic should be 0. And then the only possible solution is a torus. Okay. But you can be also more explicit. You could say, well, yeah, Weierstrass is a bit older than Poincaré and Hopf. Huh? So Weierstrass came to elliptic curves in another way. So he looked at the complex numbers and he said, suppose in the complex numbers you have a lattice. And the lattice is a discrete subgroup that is generated by 2 independent elements. So for example, this lattice could be the set of a plus b times I, where a and b are integer. It could be like that. And then you want to look at functions, holomorphic functions or analytic functions that are invariant in these 2 directions, by translation in the 2 directions, in these 2. So when you do sine, cosine, exponential function, you do things that are periodic for one period. But now we want 2 independent ones, like this. And then there are no holomorphic functions, but you can have a function that has a pole of order 2 at each point of the lattice. So you can make a function from C minus the points in the lattice to C that sends a z to 1 over z squared plus the sum over all lambda in L that are not 0. That is what the prime means. And then you have to do this. And if you add that up, one proves that this is periodic in the 2 directions, so for the lattice. And that actually, if you take this function and its derivative, so these are very standard functions. They're just one step more difficult than the exponential function. But if you have a book on complex functions, then the function you get after the exponential and maybe after the gamma function would be these functions. 19th century functions. Okay. So and if you take these functions, you get a map from C to the plane, C times C, because here I have two functions. And that map really maps, so it's invariant under translations by the lattice. So I can say, well, it's from the quotient, I hope that, so so that's where the circle times the circle comes from, because if I have this lattice, so suppose it is Z plus, so it's the A plus B I where A and B are integral, then I'm so this C modulo that, so this is a plane, but I'm making a cylinder first out of it by taking by identifying this side of the screen with that side, right? I'm just folding it, then I get a cylinder, and then I have to do the other periodicity, then I take the 2 circles at that cylinder and I put them together. So that's why you get, this is S1 times S1, and the image Weierstrass showed is all the points that satisfy a degree 3 equation. That depends on the lattice, on the L. So he showed by complex function theory that an elliptic curve has that. And we can also argue a bit from the other direction. So Riemann also had a way to think about this. Suppose you start with a donut, with a torus, and you put a skewer through it, like this. So on your barbecue, you want to put such a thing. Well, you could turn it around 180 degrees, right, around this skewer. And what I want to say is that the quotient. So yeah, so here, well, why am I looking at this? Because an elliptic curve is given by an equation y squared equals something of degree 3 in x. So the projection to the x-coordinate x is a 2-to-1 map. For every x, I have y squared equals this thing, has usually 2 solutions. Except when my degree 3 expression is 0, and that happens 3 times. But also at the infinite, at the point at infinity. So there are 4 points on the elliptic curve where that map to the projective line has only one pre-image. And I say, well, that is very consistent with what happens if you take a skewer through a donut and you turn 180 degrees, then you have these 4 points are fixed, the others are not fixed. And so if you want to know what the quotient looks like, then you cut the donut in half like this. Then you have for each point on the donut, either itself or the rotated is on this half. So you get the quotient by doing the identification on the boundary here that you still have to do. You have to identify this upper semicircle with the lower one, because the rotation will rotate the upper to the lower. And if you do that identification, you get a kind of cigar, right? Which is the Riemann sphere. Yeah, so that is not a proof again, but it shows that it must be like this. Yeah, I'm not doing mathematics today. So that is what we should remember. We should remember that if we have a Riemann surface in this kind of thing, that is a 2-to-1 covering of the Riemann sphere that has 4 ramification points, then it is an elliptic curve. Okay, that is important. Okay, now we get to another important thing, automorphisms. So we have seen that on elliptic curves it forms a group. So we have translations. If you have a point, you can translate by that point. So you have a map, say the group of P goes to P plus Q for Q fixed. And in a group, yeah, all points are more or less equal, right? Because it's a homogeneous space, we call it. So if we do, yeah, so that is nice that you have that. You can also say, but I want to look at automorphisms in the sense that it fixes the group structure. So automorphisms not only as an algebraic variety, but also as a group. And then you have to send the 0 point to 0. So that when you fix that point, then you have very few automorphisms. So this group, if you say you take as maps from this one to itself that have an inverse and that sends 0 to 0, this is very small. Usually it has only the identity and minus the identity. That means you send a point either to itself all the time or you send it to its opposite in the group law. That means reflection about the x-coordinate axis. Or you can have 4 or 6 symmetries. And this has to do with these lattices in the plane. If you have the square lattice, so all the a plus bi, where a and b are integers, then you have a rotation of 90 degrees, right? So we also saw here that elliptic curves are actually, to give a complex elliptic curve like this, it's the same as giving a lattice in the complex numbers. And the symmetry that this lattice has it also is this, the complex elliptic curve has it. You can also have this lattice that is built up from equilateral triangles, right? And that has a 6-fold symmetry. That explains the 6. So all these points of view are very important. Now, this is maybe not good for a colloquium, a semi-direct product. Let's forget about it. But if you are interested in arbitrary automorphisms of an elliptic curve where you may displace the origin, then you have maps of this kind. You can send a point P to A of P plus B, where A is an automorphism that fixes the origin. And this A can then be of order 1, 2, 4, or 6, right, or 3. It is very restricted, the A. That is important. So this was my crash course on elliptic curve. So then we come now to Poncelet. So Poncelet was a French engineer and mathematician. He lived in the time of Napoleon. Right, you see that? Was he already, yeah, so 88, so no, but he probably has not worked for Napoleon then, because Waterloo was around 1815, 1816, so then he was 28.
He could have been drafted into the army because
Yeah,
he was old enough.
He was old enough, he was 12 in 1800, and then 10 years
20
later,
something.
yeah, so he probably was in the army. Okay. Yeah, at least, okay, good.
Of course, but Napoleon wouldn't send these people to the battles because these are smart people, you know.
He went himself to the battles, so I think he also took those people to Egypt, for example. Okay, so he worked on projective geometry, and so I got that from Wikipedia, but let's look at what he did, right? So he has a theorem that can be proved by elliptic curves, and you don't see the elliptic curves. Here is the theorem. You take two conics, so for example, two circles, two ellipses, or something that is given by an equation of degree 2 in R2, and this is how we stated it, given for a given n greater 2, if it is possible for your two conics to find a polygon with n sides that is simultaneously inscribed in C and circumscribed around D, I will give a picture, then it is possible to find infinitely many of them. So here is an example of what he is talking about. He says, here you have one conic, C, and here you have another one, D, and to say that you have a polygon that is inscribed in the C, then you want to have these points on the boundary on C. So you have 1, 2, 3, 4 sides. It is inscribed in C and circumscribed around D, because this is a tangent, this is a tangent, this is a tangent, that is a tangent. That's what it means. So if for some point P, he says, you go like this and it closes after 4 steps, then it will close wherever you start. And so I'll try to convince you that this is true with modern methods. So I made what is called the GeoGebra file. I don't know if you use that here for teaching, but this is free on the internet, this program. So you can move the point even, right? You see, if you move it, so this infinity, actually he could have made a stronger statement. He could have said any point will work, right? And this is, well, this is more or less a proof in this case for n equals 4, right? At least you see that when you move the beginning point, then it still closes. It doesn't change. Yeah, great, huh? These methods, these tools. Yeah. So, but the question is, of course, what I showed is nice, but what is the theory in this, right?
Why does it work?
Yeah. What is the theory? So, actually, Jacobi, did I give it? Okay, the theorem, he stated it and he proved it also in 1822, but 4 years later, Jacobi gave a different proof. So that's the Jacobi from the Jacobian, the matrix of derivatives. It's the same guy. So how does his proof work? He says, well, what you should do is see the elliptic curve in this. And what is the elliptic curve? Well, you can look at pairs. So you have these two conics, this one and that one, and you look at, say, a point, so combinations of a point P on C, that's a point like this, and a point L tangent to the other one through this. So we look at lines pairs of points and lines. The point should be on the line, and the point should be on C. So we should, and also the line should be tangent to the other one. Okay, so why is that useful? Because we have a map from X to C. We can forget the line, for example. Right, that's what we do. We take a point here, that is a P, L, whatever they are, we can forget the L. Then we get a point on C. And yeah, clearly from the picture, if I have a point on C, then there are two tangents, right? There is this one and the other one. I mean, the picture convinces you that there cannot be more. But, so that map has degree 2, and it ramifies, so it can also happen that there is only one tangent. And where does that happen? Well, at the intersection points of these two conics. And here you don't see these intersection points, because we only look at the real points. But if you would take complex points, you would see that there are 4 intersection points. And in those points you have the ramification. So that convinces you that this X actually is ramified, is a 2-to-1 map to this conic. But we saw at the beginning that we can parameterize a conic by the line. And so that means actually that this conic, if we do projective geometry, is a projective line. It's isomorphic to a projective line. And the projective line is the Riemann surface. And so this X here is 2-to-1 over the Riemann sphere with 4 ramification points. But that is an elliptic curve. So that is how the elliptic curve enters, right? So this X is an elliptic curve. Now, this map, what are we doing? We have 2 maps from this X to itself. If we take a line tangent to D, then it has, well anyway, a line will intersect the C in 2 points, right? So if I have a P, L, suppose I have this point and that line, then I can say, yeah, then I can also go to this point, this point and this line, then the line intersects the C in this other point, and I can go from P, well, if I call them P and P prime, then I go from P, L to P prime, L. That is what we call sigma. You can also flip the line. You can say, well, if I have a point here, P, and this is the line, then I can say, well, there is also another tangent, so let's do that. That's the tau. Then you flip the line. You say P, L gives me P, L prime. And this Poncelet thing, what he was doing is he was composing these two. He said, if you have a point and a line, then first go to the other point, and then switch the line. That is the next step, and then you do the same, and then you look if it closes. Right? So iterating this composition of these two involutions is what Poncelet was looking at. So, well, I also told you what the automorphisms of such a curve, such an elliptic curve look like, right? If you have, so we don't give this elliptic curve by an equation, but we know what its automorphisms are. And if I know that composing, so I say these are involutions, right? If I flip the point, then if I do it twice, I'm back. If I flip the line, if I do it twice, I'm back. So that must be the case that sigma of x is minus x plus some point in my group law. Then tau of x is minus x plus some point in my group law. Right? These B and C, they are just points on my elliptic curve. Yep. So what happens if you compose two of these things? Well, then you get a translation, right? If you compose this, you get x goes to x plus c minus b. That is a translation. And in a group. And if you do the first course in algebra, then you will learn that well, actually, yeah, learn how to do something like that. So if the thing closes for one given initial point, then it means that that initial point plus a number of times, n times this, is the initial point. But that is the same as saying that n times this thing is the zero. And then it will be valid for any beginning point. Then when you translate n times by this thing, you get back to where you started. So the structure of the elliptic curve explains exactly this thing. Okay?
No. All right.
Ah. Good. So that finishes the Poncelet thing. Well, okay, so there are some references here. I could say something about classical mechanics, but I'm going to skip that until that is actually something different. Here we have, well, again, somehow an elliptic curve comes up, And it comes because you get two equations in three variables. Now it is not one equation of degree 3, but you get two equations of degree 2 in three variables. And if you intersect those two, if you have to look at this, so you get two ellipsoids in R3. If you intersect them, you get an elliptic curve. One can see that that is true, and it explains a lot about these kind of, I think this is the kind of curves. If this is one ellipsoid, and if you intersect it with another one, you get a curve like these things, like these are drawn. And actually, it explains something very funny. If you have a block, and you let it rotate, you have this rotation about this axis, and you see that it rotates very nicely. You can also rotate it along the long axis, and it rotates very stably, you see. But if you try it like this, then it wobbles, yeah? It's impossible to make it just do this, right? And that is explained by these kind of pictures here, which also have to do with elliptic curves. Now, if there are questions about this, I can answer. You missed my
sorry.
classical mechanics.
Sorry, I'm not receiving the call.
Yeah, so it's quite fun. Actually, there is a bit to say because Arnold is a famous mathematician, I think. But he looks at these things always from not as an algebraic geometer at this, but he looks at it from the point of view of differential geometry. So for him, such a curve is just a circle. It's diffeomorphic to a circle, but for me it has more structure. It is not any in an elliptic curve. You can say, well, that's certainly not the same as a circle. You cannot parameterize an elliptic curve with a line. In a circle you can. So my way of looking at it gives more information about this. Okay, I want to skip this. I want to go to Escher. So you have seen this picture probably.
Not that.
Never?
One. No.
No?
The other one, the famous one, when the guy goes upstairs, the stairs, down the stairs.
That's a very simple one. This is much more complicated.
More complicated.
Yeah. Because what do you see here, right? You see some person standing in a gallery.
Right.
But something strange happens because he looks at a painting, at this painting here. But if you go around like this, you find out that he is in his own painting. Yeah, I mean, he is standing in his own print gallery. Yeah, so that is a bit strange. How did that happen? Right? And actually, this is not Escher's painting really, because Escher's painting was missing the middle part. He had put his name here somewhere because he didn't know how to fill in this chaos. But this was what my colleague Hendrik Lenstra discovered and worked out with Bart de Smet. What is the theory behind that? And so actually there is a normal painting. This is isomorphic.
That I understand. That one I understand.
Yeah, you see, but you don't see that this guy is in this picture. There is here somewhere the same print gallery where he is. Right? This is a picture that contains a copy of itself, but that is a kind of picture that you see very often. Right? It also occurs if you have two mirrors and you stand in between. You can see infinitely many copies of yourself. And here, here for this I show you a movie. So that's this one. Let me see if I can make this bigger. I don't need sound for this.
No necesita.
No, not yet. Why is it not getting bigger? Yeah.
No, you can expand it from the top corner, right?
So good, like this. Okay, look at this. You zoom in.
Okay.
And after 256 times as big, so it multiplies by 256. Where are we? You see him come back again.
Yeah, he's in there.
Yeah, he is in there, right?
Right.
You see that?
Right.
And I could do it again.
Okay.
But he's there. So this is not so strange because you know how to do that.
Right.
But this somehow you can transform in another kind of picture that is the other one, this one, which is the warped. Yeah, how would you say that?
Twisted.
Twisted.
Torcido.
Right. So let me show you this one. So now. He also comes back. There he comes. You see?
Yeah, yes.
Yeah. So that's a strange thing. And so how does that work? Let me spend a few minutes on that.
Well, you see, let me interrupt for a minute. Actually, when I was a boy, a kid, there was a famous detergent called Cleanso.
Yeah.
Okay, where on the picture of the box,
Yeah.
there was a woman holding a Cleanso, where
Yeah.
she was in
Sure,
that
sure,
holding a Cleanso. So
That's
I
this
thought-
thing, yeah?
Right. Yeah, it's that thing. So
Yeah.
I thought, oh, how is that possible? Maybe, you know.
Yeah.
So maybe that's when I decided to become a mathematician.
Okay, good. Yeah. So the question is, how do you go with this? This is what Christian says is true. This is, you see it very often on
Real life.
in marketing posters. It's a well-known trick. But this is something that Escher did as an artist, but he did not understand it. But he did it.
Mm-hmm.
And he did not do the stuff in the middle, but he knew that he could do something like this. So now what is the stuff, the mathematics behind that? So let me go to that. So here, this picture contains a copy of itself scaled by 1/256. And then we want to go to this twisted thing. Okay, now what does it mean that you have a picture? The picture on the plane is nothing else than a function from the plane to the space of colors. Right? Every pixel should get a color. That's how it works. So as a mathematician, we can model this with a function, right? And to say that it is C cross stands for the multiplicative group of the complex numbers. I mean, I don't care so much about one pixel, the origin. No, because I want to reveal some structure. The fact that this picture contains itself under magnification by a factor of 256, so the self-similarity is expressed by this equation. Yeah, that the value Q was this 256, right? So that is the self-similarity. So when you became a mathematician, you could say it much more simply. Yeah. And so now, if you are a mathematician and you see that you have a function on some set and it is invariant under the action of some group, you should say, okay, it defines a function on the quotient of the set by the action of the group. That is this. And I claim this is an elliptic curve again. So there is your elliptic curve. So why is that? So I think that I can give two reasons. So you can say that in the complex numbers, if you take all the complex numbers whose absolute value is less or equal than 1, but greater or equal than 1/256, you have the outside is a circle, the inside is a smaller circle, and this multiplication will glue the outside circle to the inner circle. But that gives you a donut, right? That is an elliptic curve, and at least a torus. You can also say, well, we have this, we can even, so we know that an elliptic curve is the complex numbers modulo a lattice. And we can also cook up this lattice, because you can say, well, C star is the image of the exponential map. We can say from the complex numbers to the non-zero complex numbers, we have the map Z goes to e to the Z. And this says, for people in algebra, you say this is a surjective group homomorphism. The kernel is 2 pi I Z, so C star is this. It's the quotient of C by the additions by translations by 2 pi I Z. And so if I divide this moreover by Q to the Z, then I have divided these complex numbers by two things, namely first the translations by 2 pi I Z, and then the multiplications by powers of Q. But if I do that, if I pull that back, say, to here, it is additions with multiples of log of Q. So I have inside the complex numbers this lattice. This is precisely the lattice that gives this thing as a quotient. And then the whole trick that Escher did is to say, well, now we get, so instead of saying that we go to the quotient and we get just any picture, no, we go to what is called the universal covering of this C star, and we have a picture, F tilde, that is invariant under both translations. But now is the trick, we can take any point in this lattice and first divide out in that direction. So this is the double invariant picture, not very, I don't know, it's not very appealing. But it has the two, you see that this goes to that, but also this goes to that. It has the double invariance, right? And now what you do is you divide out by one that goes from here to here, I think, first, right? If we want to go back to the picture the straight picture, then I think we divide out by the vertical one, that is the 2 pi iz with the exponential map. But now we do something else. We say, well, take just any non-trivial combination of these two, like this, and call that Z1. And then you say, I want to divide out that thing. So you do Z goes to e to the az, where a is 2 pi I over this. Then this map divides out the translations by the Z1. Yeah, because if I consider for Z Z1, then I get here x of a times Z1, but a times Z1 is 2 pi I, that is again 1. Yeah, that is how you do this. If you take that map, then you get precisely the picture that Escher made. Yeah, so that is somehow it is a transformation that is perfectly understandable if you do this exponential or log thing. And you can read much more about this on the web pages of the Smith and Lenstra, if you want.
But Escher was not a mathematician.
No.
He was just a
He was
painter.
an artist. Yeah.
An artist.
Yeah.
And he imagined all these things.
Yep.
Oh,
And
amazing.
people did not discover this elliptic curve until 2002 or so. Very strange. Okay, so it is okay. Let me go to the last part. This was the game, the goal of my lecture. So let me do that in 10 minutes. So there is a museum in Bilbao, Spain, Guggenheim Museum, where on the ground floor you have enormous sculptures of sheet metal. And these are thick things, right? Here is a person, you see how big this is. So let's and I walked there also. I came there in 2013 in the summer for my vacation, and I was walking here. And I thought, well, this is not so. This was a bit random to me, right? I mean, that is not. But this is not a random thing. These are not random. These. I mean, you can see a little movie where the artist explains what he has done. So let's look at that movie. Now maybe the sound would be good. Where's my sound?
Hay que poner el sonido ahora. Rodrigo?
It's gone.
Está encendido.
Well, maybe
It's on.
it's on. Okay, let me try. No, but I only have to turn the volume on. I can do it. Let me do it. Okay, it's this one, right?
16 minutes.
Yeah. But let me. Okay. Good.
No, don't touch it.
No?
It's on.
Yeah, but the volume is not high enough.
No, but you have to. Yeah. Now play.
Okay, yeah, but let's see. Okay, maybe.
To give form and shape to the entire space.
Okay, this is
And
the
that was
Sarah.
done through placement, through trajectories, through gravitational vectors, through different notions of durations of time and how they spin out from solid to void into each other. Beforehand, we had a logical way of setting these up in relation to the long axis, not in relation to how people would go independently, because people will go where they will. For instance, there are 3 pieces here in the opening as you come through the door that leads into it from the atrium. I think we'll walk to the single piece first. because it really is the key to understanding everything else that's going on here. If you look at the ellipse on the floor, might be best if the camera just passes it around there. If you look at the ellipse on the floor, and you follow the ellipse on the floor, you see that its long axis is running this way, and its short axis is running this way. If you look at the ellipse in the air, the top of the steel, the long axis is running this way, and the short axis is running this way. The radius of this form is exactly the same as the radius of these forms. These are identical. There's no change in radius as it turns. This is the basis for understanding all of these pieces.
Okay, so that's where I stop him. Yep. So we have seen how he explains what he has done, or he explains partially. He uses artist language. He talks about gravitational vectors and what else, how you experience time, but okay, you can forget about that. He had two ellipses. He said that on the ground you have an ellipse, and at the top is also an ellipse, right? And that's a mathematical statement. Right. And he also talked about the long and the short axis, so that these two ellipses, these two axes are not in the same direction. That's the whole thing. You also see here that when you look at such a surface, that the contour is a straight line. So that means that actually, if you think about why the contour is a straight line, so he says, okay, I took an ellipse there, I took an ellipse on the ground, and then I make this surface in between. And how does he do that? By taking the convex hull. He takes the convex hull, but that is the only way to get the contour, no matter how you turn around it, to get it straight lines. You take the convex hull. You can also say that in another way. If you look at it, there is a plane, so you see a line, and that corresponds to a point on the upper ellipse and on the lower ellipse. And there is also my eye, and these 3 points in space determine a plane. And that plane intersects the horizontal plane here at the top in a line. And that line is a tangent line to that ellipse. And on the bottom it's the same thing. So you join by a line points on this here, where the tangent line to this ellipse is parallel to the tangent line of the bottom ellipse. That's how it works. So that was my understanding of his video, but then I wondered, but what kind of surface is that? Can it be given by, is it something for me as an algebraic geometer, right? Is it an algebraic surface? Is it given by a polynomial equation? And after I left the museum, I spent maybe a night or so, to find the solution. And I think it is, here we have it. So here is the convex hull. You have this thing. Oh, and later I discovered also that he described it in another way, which is quite different. So let me also show that to you. That is actually very funny, because you also get, it's this movie.
Let's do it in different ways. Cezanne did it his way. Obviously, Pollock did it his way by dripping downward.
He says he doesn't like academic people.
But I think what's interesting about artists is they
because
constantly
artists
come up with ways of informing themselves by inventing tools or techniques or processes
just do things
that allow
with the
them
artist
to see
invents.
into material manifestation in the way that you would not if you dealt with standardized or academic ways of thinking. These ellipses only came about because he invented a wheel to make these things in order for us to understand.
You see here.
It's a small invention, and on another sense, it has never come up in the history of form making before. We're not drawing the outside of the piece like a pear or a donut. What we're doing is trying to figure out what the internal volume will revolve like. We made a wheel to figure that out, and that wheel predicates the outside of the skin. So it's the way of working from the inside out.
Okay, maybe I should.
What's his nationality?
I think
He's
one
American.
constantly tries
He's
to
American.
invent ways of seeing into what others doing, so
Yeah, you see here
don't
is
get
this
some lockstep
thing,
notion
right?
of how to do what
Right.
you do.
Yeah, so, but you also saw that here he has
Not
this view.
drawing the outside of the piece like a
And now-
pear or a donut.
Here in the back, he has already these things. So what does he do with his wheel? He puts his wheel on a sheet of zinc, and he just, well, but it should be not too hard, because you want to roll the wheel there so that it picks up this metal. You can also say put glue on your wheel and put paper on the floor, right? And then roll. And then you get a surface. And that's the surface that he has. So you get it by rolling something like
He says no one else has done this before?
he says no one else has done that, and I believe him.
Yeah.
Well, maybe by mistake. You see, if you want to make a car, you make circles, right?
Yeah.
And you go smoothly. Now I remember the Flintstones. they had something more like a wheel like this, right? I mean, so maybe he was not the first, but it was never practiced as art, yes.
Right.
So maybe if you roll the trunk, yeah. Well, but maybe a tree also does this somehow, because if you, but is a tree convex? Does it have ellipses? I don't think so. The tree is more like a cylinder. Okay,
Right.
good. So he has also this wheel. Well, so here are my findings as a mathematician. So yes, it can be described by a polynomial equation, but in half somehow. I will explain why it is only half. So I claim that there is an irreducible polynomial there. So actually, this f, you have no choice, of degree 8, which I computed in two ways, so that the surface that Sarah makes is half of the set of zeros. And I never computed such a polynomial, but I know it exists, of degree 8.
But it's degree 8 and 3 variables.
In 3 variables.
So it's probably not very easy to find.
Well, that's linear algebra. You see, how many monomials are there? It's something big.
Yeah.
Maybe 200 or so.
Yeah.
So a computer can do
The
it.
computer can do it.
Yeah, I don't know. So that's why I didn't do it, because if you get this thing and it fills a page, then what do you see?
Yeah, nothing.
But I know it exists, and that it has degree 8. But you can say a bit more. So why is it only half? And it is because so when you, if you remember, I said you have these two ellipses, an ellipse in this plane and an ellipse on the ground. And you have to join, if you take a point on the ellipse above, you have a tangent line, you have to look for a point on the bottom ellipse with this parallel tangent line. But actually there are two. Because if a point on an ellipse, opposite points have parallel tangents. And if you do the symmetry by the center of the ellipse, you get parallel tangents. So that is what he did not do. So here comes a picture, I hope. Here is the picture. So now it's mathematics. I parameterized it. And so this is the one that more or less as is in the museum. Here the long axis is along this line, and here it is along this line. So I rotated 90 degrees. So in the museum it is less. But so this, you see, draws a line from this point here to this point here, where the tangents are parallel. But you can also take the point at the backside. So take this point here, goes to that point there. There is this tangent. But here you have a point with a parallel tangent, and that's what happens here. Here you go to the backside. And these things. So this is also some nice feature of algebraic geometry. If you take any polynomial that is 0 on this, it is also 0 on that. So you cannot separate them with polynomial equations. They are Siamese twins.
If you separate them, you kill them.
Hmm?
If you separate them, you kill them.
Yeah, well, I mean, you simply cannot. Maybe with analytic tools, yes?
Yes.
But not with algebraic tools. So here you see them together. I made the outer one a bit transparent. And I tried to explain to the artist what I had done.
Good luck.
But he was interested, by email. So I had some email contact with him. He was interested, but I could not get him to understand. But I think now, a year later, somehow, I have a better way of explaining it to him. So what time is it? It is an hour after my beginning. So maybe I did not explain. I'm talking about this also because I discovered my elliptic curve in this, right? So it's the same thing as above, as before, like with Ponsonnet or with other stuff. So there is an elliptic curve because, let me do it like that. You have these two ellipses, C1, C2, and the planes where they are in are called H1 and H2. And if I have a point Pi on Ci, so P1 on C1, then T, this is the tangent line in the plane to that. And so I'm going to look at this set. You take pairs where P1 is in C1, P2 is in C2, and the tangents are parallel. And I claim that is an elliptic curve, because you can exactly do the same. You can make a projection. You can forget the point P2, and then you see for every P1 there are two possible P2s. And you only have to see that this is so it is a 2-to-1 map to the first C1, and that is a Riemann sphere. You have to see that there are 4 ramification points, and that is not a difficult thing. So you do some projective geometry. I will not bother you with it now.
But have you found the Weierstrass equation for it?
No, I never bothered to do that. I mean, why would I? Yeah, well.
Might be interesting to see what.
Well, then I have to have a student, yeah? I mean, you don't do this yourself. No. That is not good for a professor. So such a computation, no, that I will not do. What is interesting to note is that if you take the real locus, the real solutions to this elliptic curve, then you see that it is not with one. So in the beginning we had this picture with an egg and a branch. It had 2 parts, and that's what happens here. This is one part is what he had in the museum, and the other part is what is not in the museum. And I also have a suggestion of what he should do next. So he should actually. So here you see the blue thing is in the museum, and the yellow actually should also be there, I think. If the museum would be, say, 5 times as high, and you would extend this blue thing, you would get these kind of singularities. And this looks a lot like the singularities that this one has in the middle, the yellow one. So actually, the blue and the yellow, if you extend it infinitely in projective free space, there is actually an automorphism of this thing that interchanges the blue and the yellow. So they're not also really they're Siamese twins with identical DNA, of course, right? They are the same. So that is so projective geometry does that for you. Well, okay, let me not do that. It is you can also do a little bit of differential geometry with it, Gaussian curvature, and then there is a theorem that indeed says that these things roll. You can roll them on a plane, so that indeed this goes back to this Serra thing, how he made them. Also mathematically, that makes sense. These surfaces as Riemannian surfaces, so with a Riemannian metric, are locally isometric to the plane. Because, well, for some not too hard reason. So that's it, I think, right? So I actually also 3D printed this new thing, the blue and the yellow together, because that's nowadays very easy. You have to find somebody who converts your Sage output to a 3D printer, but that is this guy Oliver Labs. So here I advise you to look at this as marvelous mathematical art. You can buy nice things for 30 euros.
Can you send us this?
I will put it on my website. You can look up. Yeah. So that is. So in the old days, you see, mathematical libraries had a series of surfaces made of plaster. But now you can have them 3D printed. They're much nicer and cheaper also. So that is a
Cheaper.
good
It's not free?
cheaper. Well, I bought a cubic surface with 27 lines for 27 euros.
Ah.
And this company may have a printer on in South America, right, or in Chile. I don't know. I had to buy it somewhere in Germany, but it was printed in the Netherlands and then shipped to me. So the shipping was not expensive.
So you have that model in your office?
Yeah. No, in my house, at home.
Oh, okay.
So a few thanks, and that's it. Thank you.
Questions, comments?
Seems that we made all the questions, asked all the questions, and made all the comments during the talk.
Well, who knows?
It's interrupted a lot.
I'll put the notes on the web so you can. These 3D things are nice.
So what is the attitude of this guy, Sarah, with respect to your mathematics? I mean, is he willing to try to understand things? Or?
Well, first he was interested, and I sent him an email, and he replied. And, I tried to explain it, and
He gave up.
He gave up.
well, I even gave him a 3D print of this thing, but I don't think he understands.
Right.
And that is not his fault, it is because I could not explain
I
it
guess so.
easily enough.
To a non-mathematician.
Yeah, but nowadays I think I have a better way of doing it. You can also, so one way to do it is to say, well, take his wheel, right? Take his wheel. But now, instead of putting it on a sheet of paper and then rolling it, you put one of the two wheels on top and the other one you somehow force it through the paper and below. And then if you turn, you will get the yellow part. But you have to put one wheel on top of the paper and the other one below. This is also not so easy because you have to make a hole then. But that's the idea. And the idea is more generally, if you take one ellipse, say, and so somehow you have to take two ellipses in space. It doesn't matter how, but you fix them together and then you roll the result on a paper. Then you can, so if you just make these ellipses, if you put them in another way in free space than his, you can get anything. But you also get the yellow thing. So for example, I would be interested in getting somebody interested who wants to make tents. Because these would be very nice tents. If you go back to the picture, for the yellow part, here, if you just remove this upper part here, but you just look at this, right? That would make a marvelous tent without angles. And it's very easy to make. You take this ellipse here, there is an ellipse here that you see that goes inside. If you roll if you just take the convex hull of these two ellipses, you get this tent. So actually I think there should be
a tent without corners.
A tent without corners. So also it will not break that easily, yeah?
Let's see, well, you have to see whether it's wind resistant or not.
Well, it's good enough. It's as good as any tent. Only it lives longer. Right? But my aim in life is not to make money, but
yeah.
But I would like to see somebody make that, right? So maybe if I have another student, so instead of making the equation, I'll ask him to make me such a tent. Yeah, and then try to get some company, go get some company interested in it.
Company.
Yeah.
Interesting.
Yeah.
Okay, thanks again for this amazing talk. I'm thinking really changing my research area.
To what?
It's more interesting for me.
Okay.
Yeah. But
thanks.
She wants to know what's the scientific collaboration that prompted your visiting me here. We discussed some mathematics, I guess, some time ago, right?
Yes, that's certainly true. So, should I take the microphone? Yes. So, I was planning a trip to South America, and I wanted to visit people I know in South America. So I want also to learn some people, to get to know some people in Rio. So I go to a few places now. So Rio, and then La Serena, Santiago, and then to a conference in Montevideo to finish. And so, I thought of Christian here because he has been 2 times, I think, to the Netherlands, where I invited him, and it was always my intention to visit him someday. Right? To come here to visit and have some discussions here about the kind of mathematics we do.
Okay. Entonces, el profesor Bas Edixhoven mencionó que él que tenía intenciones de visitar Sudamérica. De hecho, estuvo un día en Río de Janeiro, dio una conferencia en el IMPA, Instituto de Matemáticas Puras y Aplicadas de Brasil, y también estaba interesado en visitar matemáticos que trabajaban en Sudamérica, en particular en Chile. Él, por supuesto que quería conversar conmigo de algo de matemáticas, porque yo he visitado Holanda en 2 ocasiones y él en algún momento prometió devolverme la visita, lo cual cumplió. Y también él va a dar charlas en Santiago y en Valparaíso para hablar sobre lo que él hace. Y bueno, y eso es esencialmente el objeto de la visita. Además, él va a asistir a una conferencia en Montevideo. Él va a salir de Chile dentro de unos 10 días y va a participar en una conferencia en Montevideo. Por lo tanto, va a cumplir su objetivo de visitar a varios matemáticos latinoamericanos y hablar de su trabajo y aprender también de lo que nosotros hacemos acá. Y tenemos mucho en común porque trabajamos en un tema análogo.
¿Pero en este momento tienen pensado trabajar en algún
proyecto futuro?
Juntos, quizás?
Okay, she wants to know if we are planning to write a joint paper sometime in the future, maybe?
Well, that could be well possible, yes.
Dice que podría ser posible, aún no está claro, pero podría ser posible.
Maybe it's good to say that the first collaboration we had was on this SGA1 volume. So there I was looking for people to work on some book, and Christian contributed a part to it.
Okay. Yeah. Él, en algún momento, en el pasado, él formó un equipo para trabajar en un libro, y yo colaboré un poco con eso, y eso fue algo de colaboración que tuvimos en el pasado.
Comentaba que era la primera vez que venía a Chile, a La Serena y también al continente. ¿Qué le ha parecido a La Serena lo que ha podido conocer hasta ahora?
Okay, so she remarks that this is your first time in Latin America, and she wants to know your opinion about what you think of La Serena, the region here.
It's beautiful. I like the climate here. In my continent it is now winter, yes, cold, and here it is much nicer today and yesterday. We had good weather. I like the food. I have not seen the university so much. I can work here, but I have not seen students to interact with, right? So I would be curious to see what students here are.
Okay, el profesor Edixhoven dice que le ha gustado mucho aquí La Serena, que el clima es muy bueno comparado con el clima en el día actual en Europa, que es en invierno, ¿okay? Y entonces le ha gustado mucho el clima, que ha tenido días soleados, le ha gustado la comida, y que no ha trabajado mucho aquí en la universidad, que le gustaría conocer estudiantes si es que tiene la posibilidad en el poco tiempo que le queda.
Finalmente, ¿podría por favor enviarle un mensaje a los alumnos que se están preparando para ser matemáticos acá en la Universidad de La Serena?
Okay, so she would like you to maybe give a message to future mathematics students who might be interested in joining the math department here in La Serena.
Can I think a little bit?
¿Puede pensar un poco, un mensaje, a message, for like encouragement?
Well, maybe I should say mathematics is a beautiful topic. It is quite different, I would say, from other fields of study, because mathematics is some people say it is the biggest intellectual construction of mankind. So it's something where you do not need big machines, or, nowadays we use computers, but mathematics, if you like thinking yourself, then mathematics could be very nice for you.
Gracias. Entonces, el profesor nos dice que matemáticas es una de las más grandes construcciones, o la más grande construcción intelectual del ser humano, que es algo que ayuda a pensar y que no necesita muchas máquinas. Bueno, ahora tenemos computadores, dice, pero esencialmente si a usted le gusta pensar y puede trabajar en matemáticas, que es una gran construcción intelectual, una de las glorias del intelecto humano.
Maybe another message.
Otro mensaje.
Yes, but I would say that everything I learned in mathematics, I have been able more or less to apply in everyday life. Not only in mathematics, but only you know how to think about things. So when I buy a house and I have a loan from the bank, I can check that they don't cheat on me. And not many people can do that.
Dice el profesor, dice que él ha tenido oportunidad de usar las matemáticas de una manera aplicada. Todo lo que ha aprendido ha podido aplicarlo y, por ejemplo, él tiene la capacidad que quizá no todo el mundo tiene de determinar si el préstamo que le ofrece el banco para comprar su casa realmente está bien hecho o lo están engañando. Es una de las cosas que se aprende al hacer matemáticas, a pensar por sí mismo. Okay? Thank you. Gracias.
Okay.